have Joanne here for first Jing seminar of today, and coming from work, right?
Yes.
Like our second speaker today, actually, by pure coincidence. Sometimes things work out nicely. I don't think he's here.
No,
yeah, I'll be here later. Anyway, so Joe will be talking about steady states for BGK, so take it away.
All right. Yes, so I gave a very mysterious title. Thank you for coming. I hope, yeah, this is going to be very light. So this is a joint work with Angeliki, who's in IHS, ES. And some of you might have met because she was here on the program a month ago or something. So basically, I don't know if you have, if you are a kinetic person or have been to a lot of these talks, you know that we are looking at studying the evolution of the density of a typical particle in a gas. So I guess there'll be some weird particles, but so this unknown is f of t xp, and for each t, this is a probability density function on x and b. So x is space, b is velocity. So, I mean, this is a very classic setting of kinetic theory, but I guess some of you guys are fluent people. So we have an ensemble of particles which interact with each other in some way. And then we look at the density of a typical particle, and we imagine that most particles will be typical. So the kind of, I suppose if you look at where the particles are, they are likely, you know, there are more particles where this function is large and less particles where this function is small, or, you know, specifically they approximately obey this, look like they're distributed according to this density function. So that's our unknown, and in kinetic theory, we usually look at evolutions of this unknown according to different equations, I guess most famously Boltzmann equation. Normally, I don't know if this is quite the right word, but normally in the sense of the equations that are normally studied by kinetic theorists in my community rather than normally in the world, you will have an f t xv, and as time goes to infinity, in some appropriate sense, to Gaussian in velocity. So the velocity marginal of this, so where so that's the Gaussian, and then T is the temperature, and U is what I would call momentum of the Gaussian, because it's velocity, so the average, the mean of the Gaussian. What this rho function is will depend on exactly what your model is, but I'm thinking about looking where these spatial the behavior is. So say we're on the torus and there's no fancy things going on in space, then it's just going to tend to be inhomogeneous in space and Gaussian velocity. Okay, so this is the kind of typical situation in kinetic theory. You end up with Gaussians for your velocity marginal, and this is
stupid.
Yeah, of course.
Why is there any reason for this?
Well, I'm about to tell you.
Okay.
So it's basically because the evolution increases entropy. And fixes momentum and second moments. So it fixes the first and second moments, and Gaussians maximize entropy.
You are talking about.
Yeah, so I guess I'm trying to be super vague here. So for Boltzmann equation, you have Boltzmann's theorem, which shows that the equation dissipates entropy. And you know, so if you fix what your model is, then you can prove this kind of fact. And in general, if you have a model which is in some way representing the physics of the problem, you expect it to dissipate entropy and preserve your, you know, so preserving momentum and preserving kinetic energy will correspond to preserving first and second moments of your velocity marginal. And then Gaussians have the largest entropy for a fixed first and second moment. Yes, they're the unique distribution that maximizes entropy for functions with finite first and second, finite and fixed first and second moment.
It's unique in the sense it's global maximum. There's no other local maximum.
Of the entropy functional.
Yeah.
I think so. I mean, you're looking across like a function space.
Yeah, what I'm asking is that there would not be such situation that locally conversion to the local maximum. There's a convex prevented to jump to.
Oh, so the entropy functional is, I mean, so it's a function of functions.
Yeah, sure.
But it's convex, yeah.
Okay. So it's a
Yeah.
convex.
So I mean, it's a bit more complicated when you have a spatial variable because there's something going on in the space thing as well. And you know, it's possible. It's not, once you know that your evolution increases entropy, it's not immediate that you get a Gaussian, because even though it increases entropy, it doesn't necessarily have to increase it to the maximum. You have to prove that that's going to happen. You know, so people prove typically that you're not in a Gaussian. If you're not in a Gaussian state, then you will continue to strictly increase entropy. Okay, so the reason I'm telling you this normal situation is because I guess the broad setting of what I want to talk about is when that's not true, when we're not converging to a Gaussian at velocity. So I want to talk about non-equilibrium steady states. So this is basically when you have some external action on your system which breaks the monotonicity of entropy along the flow. So typically you're in a non-closed system and you have some energy coming in and coming out, which screws up your dissipation of entropy along the flow of your equation. So I'm going to talk about a specific example of this, but I guess this is kind of like the macro picture is looking at when you don't have nice Gaussian steady states. Okay, so what I want to do is when we have thermal walls, so here's the picture is we have a cold wall and a hot wall, and then we have a gas in the middle. So the particles, when they hit this wall, are going to come back out with a random velocity, and the kind of temperature set for this wall is going to be some fixed number, which tells you so they're going to come out more or less with the Gaussian distribution, and the temperature / variance of that Gaussian distribution is going to be some fixed number, and it's going to be a different number over here. So the walls have a temperature, and the way the boundary conditions work, they kind of put an external action on the system, which breaks all the nice kind of entropy monotonicity behaviors. Okay, so now I will write down a natural. Go on.
Sorry, yes. Next person, so very neutral with this. The spatial variable that you had, wouldn't the density change and would you, because of the cold wall and hot plate?
Yes, so you do, yeah.
So, okay, so I'll come back.
So F here is going to converge to something which isn't tensorized. So I mean, isn't a function of X times a function of B. It's going to converge to something complicated, and it's not going to be Gaussian in velocity in any sense. So that's what we expect. So that's one of the really important things about this is that the steady state is something where the X variable and the V variable are not separated from each other, because
So that state is like completely off.
yeah, all this stuff goes completely out the window. And this basically makes this situation much harder to deal with. And I mean, in general, people can't do very much in this situation in like rigorous analysis, kinetic theory type stuff. So we're looking at, so because the situation is hard to deal with, and we kind of want to look at like a range of problems, we try to find the kind of simplest, slightly physical situation we could to get one of these equations out. So this is why. So there are simpler situations but they're maybe a bit more contrived, but this hot wall and a cold wall is, something, if you had a very good gas model in here and a hot wall and a cold model, this is something that exists in the world. We chose a very simple model for the gas in the middle, so which is something called the BGK equation. So this is an equation that was proposed by physicists to be a kind of toy Boltzmann equation. And
What are the standard?
Bataranger, Gross, and Crook, I think. 3 people's names. So it looks like this. I'll put a 1 over kappa here. So it was initially introduced to like do numerics for the Boltzmann equation, or do numerics for something that should behave in a similar way to the Boltzmann equation. But PDE analysts and kinetic theory like it because it's much simpler than the Boltzmann equation, and people expect it has many of the same structural properties, so you can study it. Okay, so this rho F is the local density, so it's something of TNX, and it's just I'll write a U for the velocity variation because I'm integrating it. And then we also have the local momentum, so rho of F times U of F is equal to and local temperature. So I mean, this just tells you the mass, mean, and variance of the velocity motion.
Have you
Don't think so.
in the energies, kinetic energy, plus in the
Oh, right. So this isn't kinetic energy. It's. I mean, so you could write it maybe more like this. It's the. I mean, so the preservation of the. I mean, U squared corresponds to kinetic energy, but yeah, there isn't. This is just the variance of the velocity, and then M U F T F is just the Gaussian with that So that's just the Gaussian with the same local momentum and energy, local first and second moments for each x. So this equation is kind of very obvious that it's pushing you towards Gaussians. Because this is a kind of nonlinear operator which projects you onto the closest distribution, which is Gaussian in velocity, up to preserving your conservation of momentum and conservation of energy, which you do by preserving the first and second moments in velocity. So it's kind of super clear because this operator is literally pulling you towards the manifold of Gaussian, right? So it's super clear that this is kind of pushing you towards a Gaussian. So then we have some boundary conditions which represent our hot and cold wall, which is what's going to break our Gaussianness. So we have x equals, so we put, sorry, I should write down the state space. So we have x is in, we're just working in 1D. You can extend this to work in a kind of slab where you just make everything uniform in the other variables. But 1D is fine, I think. And B is in R. And you just, so then our boundary conditions is when x equals 0 and v is greater than 0. So that's the cold wall where the velocities, yes.
But to derive this equation, Boltzmann equation, you have made approximations in the collision kernel.
I mean, sorry, it depends. It's actually what you mean by derive from the Boltzmann equation. So you can get it from the Boltzmann equation. So do you know the Trotter-Kato formula? So yeah. So just by doing some approximations in the Trotter-Kato formula, which make the collision process in the Boltzmann equation happen much faster than the transport process in the Boltzmann equation. So then, so this is kind of what happens when you have very, very fast collisions relative to how much your transport is. Yeah, I mean, I probably should have explained this equation a bit more, actually.
What is kappa?
So I would call kappa the Knudsen number, but I'm frightened because there are some real fluids people here, and I'm not sure how much it has any actual.
Can you say it again?
Knudsen number.
Okay.
I'm not sure how much it really is the Knudsen number. This is not a physical. This is not a physical equation. It's something that's come up with to have the same structure and similar behavior. So yeah, but I should have, sorry. So before I start talking about the boundary conditions, maybe I should just say, so we talked a bit about this right-hand side represents somehow the interaction between particles, and it's pushing you towards Gaussian distributions in your velocity. So, and it's doing that in a way that preserves your physical conservations. And so the right-hand side is very kind of unphysical, but that's also what the Boltzmann collision operator does. And it's also, the Boltzmann collision operator is a kind of non-local, non-regularizing operator most of the time, in the same way as this operator is.
Is it the hydrodynamic limit of this equation is the same as the flexible Euler equations?
Kind of, basically, yes. So if you do like the, what's it called, thingy expansion, you get Euler, and then you get Navier-Stokes, but you get a different viscosity term in Navier-Stokes for the second order in epsilon. This term, I guess, maybe a lot of you will have seen before, is just to do with the fact that you have free transport paths. So I call it the transport term, and it just tells you that your distribution of particles is changing because they are traveling with their velocity in in the direction given by the velocity. So that means they're kind of carrying. That means that the different local temperatures, momentums are being kind of mixed up.
Do you happen to know the hydrodynamic limit? What's the equation of state for the pressure?
No, sorry.
Okay, no, it's okay. I just
Yeah. You can. I mean, so I think that the original physics paper it was designed particularly to have the same hydrodynamic limits and a lot of the same stuff. So I'm sure they have done. Yeah. I'm sure they have done that in the physics paper if you look it up. Okay, so boundary conditions. So it's something we call diffusive boundary conditions in kinetic theory, which means that your particles come in, they hit the wall, and then they exit with a distribution which doesn't really depend on the velocity at which they hit the wall. So, and it's a Maxwellian Gaussian type velocity. So when x is 0 and v is positive, we have f of looks like so. This kind of measures the mass of particles coming into the wall. It doesn't quite, it measures the flux of particles into the wall. So you can see, I mean, if you try and look at what the boundary conditions would have to be to conserve mass, you need to have, instead of having the mass, you need to have the kind of flux of.
Isn't mass corresponding to 0?
Yes.
Why you?
Yeah, so it's weird that you have the first moment, but I guess the easiest way for me to think about this is if you just look at, you would need to conserve mass in the equation above, you end up seeing that you need to look at the first moments in the boundary conditions rather than the 0th moments. So so then you have some thing that I would call m tilde 1 of b. And so this is just it's like a Gaussian, but it's normalized to have first moment 1 instead of 0th moment 1, and it has temperature T1. So I think it's this. Yeah, and we also wanted only to have positive velocities, so we're only considering because this is a distribution for velocities that are leaving the wall. And then for x equals 1 and b negative, we have the same kind of thing. So we have the flux of particles into the wall should be balanced. And then m tilde 2, which is the same kind of thing, the different temperature. Okay, so we have some kind of, the particles leave the wall with a kind of Gaussian distribution with a fixed second moment. And these two temperatures are different. So if the two temperatures of the wall are the same, then everything is nice. You're back in the equilibrium state and you converge to something which is Gaussian in velocity and homogeneous in space. But if they're different, everything is much more complicated. And so we wanted to study the kind of the long time behavior of this BGK equation when the two temperatures are different. So the first question, which is the question I actually have an answer to, and it's maybe a kind of basic question, is does there exist a steady state? So for these nice equilibrium kinetic equations, you don't really have to ask this question because you can just write down what is the steady state. Or I suppose Boltzmann asked this question 200 years ago, and so we don't have to answer this question because Boltzmann already did it. But as I said, the steady state for this kind of equation is going to be a lot less explicit and a lot more complicated. So we have to find it kind of implicitly through some fixed point argument rather than being able to write it down. And because somehow we have this non-equilibrium external action which breaks a lot of our monotonicity properties. Okay, so if you're finding a nice steady state, you might hope it was the minimizer of something or the maximizer of something, like the Gaussian is the maximizer of entropy. But because nothing, there are very few monotone quantities, well, there are no monotone quantities, there's just mass that's conserved for this equation. You can't really find a steady state as in some variational way looking for the minimizer or maximizer or something. I mean, I guess it's a kind of constrained entropy minimization problem, but no one knows how to do that as far as I know. So we use a fixed point argument. Halfway through. Going a bit faster than I expected, but I don't feel like I mean,
If you ask more questions.
no. I feel like I'm slightly knocked out today, so ask as many questions as possible and it will keep me awake.
So maybe to slow you down, makes sense what you want. Good question. So when you're talking about steady states, should I sort of interpret the non-equilibrium steady state as a constant current of particles? Because you've held the two walls at fixed temperature. And so, another way to think about it is use Fourier's law.
Yes, yeah. So this
Think about
part of the interest in this is kind of deriving Fourier's law from macroscopic particle systems.
And their dimensions
Microscopic.
must play a role, right? I mean,
Yes,
because
yeah.
Fourier's law is sort of dimension dependent.
Yes, so
In terms of conductivity. Yeah.
I guess looking at Fourier's law is maybe beyond the scope, more complicated question. But I guess, right, what would be very nice is to kind of understand Fourier's law going from a kinetic equation with these kind of thermal boundary conditions. Starting with the BGK equation, you're already maybe doing something bad for a program of understanding the way Fourier's law arises from a more microscopic model, mesoscopic model in kinetic theory, because you're taking a very unphysical model. You don't know what role the bits of the physics you've thrown away are going to play in the thing. But yeah, exactly. The reason these non-equilibrium steady states are interesting is because they have some kind of current going on in the equilibrium. Yeah, so obviously in all equilibria states, the individual particles are moving, but in these equilibria states, the individual particles are moving in a qualitatively more organized way, which has something to do with how heat is transferred from,
Because on average, they would be moving from 1 to 0.
Yeah, so I guess at every point in the steady state that we find, you have zero momentum. So it's not like they're all, I mean, obviously they can't all be heading, to the right, because then they would, yeah. But yeah, there are points where you have fewer particles and points where you have more particles, because the pressure is constant in the models. And I guess the faster particles are moving more towards the hot place, and that's somehow, well, okay, that doesn't quite make sense, but yes, I don't know. I should really have thought more. I haven't thought enough about what like the steady state tells you the individual particles are doing. Okay, so
Can I ask me? Because yeah, okay, I'm doing fluid equations, so I try to understand one of the difficulties for equations is basically is what exactly is the second order term in the equations.
Yes.
The diffusivity and
Yes.
viscosity. And two is how do you propose boundary conditions? And that's the next question. One of the important questions to ask it. So in your case, this boundary condition, if I understand it correctly, it means that the temperature of the boundary is fixed.
Yes.
And the density, the mass, total mass is conserved as the flux term.
Yeah.
The bracket. What does it tell me about the boundary condition for momentum? Does it have a boundary condition for
Basically, it's fixed to be 0.
fixed to be 0 in this case? How do I interpret? Oh, because the Gaussian is.
Yeah.
Okay, thank you.
Yeah.
So basically, in terms of if there is a fluid hydrodynamic limit, this set of boundary condition tell me that on the boundary, velocity is 0, which is literally boundary conditions. The temperature is fixed to T, which is T1 and T2.
Yeah.
Okay, great. Thank you.
Okay, yeah. I probably don't know enough. I mean, actually even formally taking the fluid limit of these equations where you have non-equilibrium behavior is very complicated. People do it, but I mean, I don't know. And you have to look at a boundary layer because different things will be going on. So I'm not sure, this is what it means at the kinetic level, but I'm not sure.
I mean,
I don't know enough about it.
Boltzmann, you can impose this kind of.
Yes. Yeah. So this is the typical one you would impose for Boltzmann. Yeah.
Okay, thank you.
I mean, okay, this is not the most physical one. You would have a mixture of this with specular reflection. I mean, this is what I don't think we didn't do that, but I don't think it would actually really make any difference to what we did in the theorem in the end. Yeah, I mean, the really unphysical thing is BGK. Actually, people can do the same kind of thing for Boltzmann. The reason we wanted to do BGK is because we want to try and answer more questions, which we haven't yet done. Okay, so our theorem is.
No, I think I need to clarify myself because one dimensions, the impermeable boundary conditions equivalent to saturation. So it's not clear. Yeah, okay, never mind.
I really don't know enough about how you take the fluid limit from these kind of equations because I know it's complicated. You have to do some kind of boundary layer approximation. Okay, so we have two conditions. So we say the T1 is less than T2, and you just have to choose which one is cold and which one is hot. And then we have some, there exists a computable constant. So actually we think we can relax these conditions now, but it's not written in a paper, so I don't want to say it's true. We need this first condition. So this is something that makes sense in terms of the model. It basically tells you that the boundary terms are big compared to the nonlinear collision term in the middle. So if kappa is big, then I've rubbed off the equation, but I will write it again. So if kappa is big, then this line is small, and if the temperatures are big, then the boundary is putting a lot of energy into the system somehow. So this tells you that, and the boundary equations are linear, so this is telling you that the linear part is somehow dominated. So this is an easy situation. So gamma 1, oh sorry, this computable constants are 1, 2, yeah, they're just numbers, they come there. zeros of some equations with logs and stuff in, but yeah. Numbers that are not particularly big or small. And then the other one we need is definitely not something that is needed for the conclusion. So we basically need the two temperatures to be separated enough. This is just a technical thing that comes out of our computations. It's very annoying because obviously there do exist steady states when the temperatures are close. They're the nice steady states. But we just, at some point, okay, I mean, I will explain a bit later maybe why we need this thing, but it's super annoying and we think we can relax this now because we're trying to do this whole thing in not a slab, in a complicated convex domain. And so we had to try and do lots of other things. And we think this is now not necessary. But I mean, this is what we have in our paper. So then there exists a steady state. We don't know it's unique, but we know it exists. And we can say some things about it in the regime where the where this kappa squared times T1 is large. So we know that 1 minus these are just more constant. So the local density is kind of asymptotically going to 1 as you get towards the regime where the boundaries are much larger than the gas on the inside. So this is not the fluid. This is like the opposite of the fluid limit. So in the fluid limit, you expect the temperature profile to look roughly linear between the two walls, and then the pressure is constant. So rho is like 1 over a linear function, an affine function.
You have temperature difference, you expect temperature to be, you don't expect density to be constant.
No. But when the temperatures are very large, the density is constant. So in this case, actually, we expect it to look kind of like, I can't remember, like this. So it has a kind of, so it's like flat in the middle and then it has kind of boundary spiky bits.
That's density.
Yeah, that's what the density looks like. So this is in like the opposite limit of, this is really far from the hydrodynamic limit, really far from the fluid case. So when you're having slow collisions, so you're far from the fluid limit.
I think it's between, it's not too far, but not too close. Because if you fix T1 and T2, then in kappa is condition 1 say kappa to be large, 2 say kappa to be small. Kappa to be between, for fixed T1 and T2, kappa to be between two numbers.
Kind of, I mean.
Yeah, and if I think kappa go to 0 is a hydrodynamic limit, then they have to be not that fluid, but not too far.
Yeah, I mean, remember this condition is kind of fake.
It's fake.
This is definitely not necessary for the conclusion. And
what gamma 1 and gamma 2 depends on?
They're just numbers. They don't depend on anything. They come from the zeros of some like algebraic equation.
It doesn't depend on total mass. That depends.
Oh, well, the total mass is fixed to be 1 in this, and because it's a density function.
Right.
Okay, and then you have your temperature, Tn, is kind of approximately, again, as this kappa times T1 is going to infinity, but in a way it's more complicated to write down, and I haven't written it in my notebook, it's approximately the like I can't remember what kind of average, but you know, the square root of T1 has to do.
Oh, I didn't know.
Okay, so this is the conclusion you end up with, and you get like the large temperature asymptotics essentially.
This asymptotic was sense, like away from London.
Yeah, I mean anywhere.
But what is the two TF? Roughly is T1.
I mean this is so you can bound it above and below by yeah. So I mean essentially it's the same. It looks the same as this.
Are they state are the steady states stable? Dynamic.
That we don't know.
Oh, okay.
We don't know. That is the most interesting question.
Sure.
Or it's actually very difficult to.
So, I'm guessing probably it's the next.
Yeah, that's the plan. I mean, it's been the plan that it's the next step for a year. We just keep finding more and more things we can't do.
This is the problem, it's presumably a dynamic history.
Yeah, that's what.
Yeah,
Right,
so-
because we have a constant current,
But you cannot
that's
say
how you
that
derive macroscopic sort of.
What you can do,
you cannot say that you have an equivalent state and you expect it to be stable. It's not absolutely.
If there are paths on both sides, yeah, you can have a constant
If there are
transfer.
what?
If your two walls are like paths, so they have infinite capacity, and so you can hold the temperature state. I mean, physically.
I mean, physically, yes.
yeah, I think
That's what we-
physically you expect these kind of things to be stable.
The stable equilibrium states. What you observe in equilibrium, what you observe in physics is already the equilibrium state.
Right.
So they have multiple steady state. So the question to ask is that they stable. So probably the unstable one you don't observe in the experiments.
I'm not sure.
Yeah, I mean, it's a very difficult question. What people can do is look. So as you go towards the fluid regime, so you can say, I am very close, my kinetic equation is in a set of parameters where I'm very close to the fluid regime. So that would correspond to kappa being very large. Then large, I think, or small. No, kappa is very small, sorry. Then at every point, your solution F will look like rho of x times the Maxwellian. This remains true, at least not maybe on the boundary, but you know, up to the boundary. And then you can find linearly stable steady states. And it's similar but more complicated to do it for the Boltzmann equation, because once everything is close to a Gaussian, everything is fine. And when you're close to the fluid regime, everything is close to a Gaussian. So, I mean, everything is not really fine. There's a lot of work to do, but you know, it's not really what we want to do is look at the case where you're not close to being a Gaussian, because then all the nice functional inequalities break. Yeah.
That's the same result holds true for Boltzmann.
So this kind of result, yes, also holds true for Boltzmann equation.
So even for Boltzmann equation, you still have that steady states.
Well, it's unknown. I mean, for this equation and for Boltzmann equation, whether the steady states are unique.
Also, we can then exist one, but you don't know whether it's not.
You don't know whether there are multiple ones, but maybe. But I think that there are not multiple ones.
Okay.
But it's really not a minimizer of a convex function. I mean, so then.
Okay, so what you're saying is that is the collision operator convex in this case.
I don't know what you mean by a collision operator being
convex.
convex.
Is in convex respect.
I mean, so the integral of this times f will be negative.
It's monotone.
It's monotone, yeah. So it's this equation is monotone. It's the boundary conditions that are breaking the.
So it's a boundary condition breaking.
Yeah.
Without boundary, we have.
Yeah. Just for the interest of time, can we?
Yeah, no. I mean, so I can skip lots of stuff now. So what's the time? So we should stop at 5:02 or at 12?
Because the classes are going on, I can just go
Yeah. I mean, it's good to have questions though, right? I mean, and the good thing about a Blackboard talk is you don't know how much stuff. It's not like you go through 9 slides. Okay, so my plan is now to tell you about the proof, but I think I will just be very brief. So basically what we do is a fixed point argument. So I'm going to rub out the equation. So hopefully you remember enough about it. So we take a linear equation. So for fixed given X. So and same value conditions. Okay, so this equation, even though it's linear, is still somehow equally hard to deal with from energy estimates or entropy perspectives, but it's easy to deal with if you take a more linear viewpoint. And so you can look at this, you can study this with Markov process theory. So this is a relatively straightforward Markov process. This PDE corresponds to the law of a relatively straightforward Markov process of a single stochastic particle, and with rate kappa, it takes a jump. It looks at its position in X, and it changes velocity to something from a Gaussian with mean 0 and variance T of X, which is some given function. So then we define a so if F infinity T is the steady state. So using Markov process theory, about which I will remain mysterious, you can show that this linear equation has a unique steady state to which you can say some things about, and the solution is converging exponentially fast in total variation towards the steady state. And I'm going to call it F infinity, and then we define a map, script F, from the continued function on naught 1 to the continued functions on naught 1, such that F of T is equal to basically the temperature of this steady state. We kind of fix everything to always have momentum 0 in this problem. So we don't need to worry about, okay, so it's a relatively, I mean, it's a kind of complicated map because you go via the steady state of an equation, but yeah. And then if T is the steady state, of curly F, then F infinity C is a steady state of the nonlinear equation. Okay, so the idea is basically the broad strategy of the proof is to study this linear equation using some probability stuff. And in some sense, this equation is even worse from the physics point of view. It's even less monotone in entropy, even less. But because it's linear, then there's a whole load of other tools we can use. And then use that equation to define a fixed point map. And so then we use a shadow algorithm, so we shadow fixed point to find the steady state of this. And Okay, so I mean, at the beginning, all the steps of shadow were hard. But let me kind of just write down the different things you have to prove to run a shadow argument with this program. So the first thing you have to prove is that F is well defined. So you have to find some space and some sense in which this linear equation has a unique steady state. So this is Markov processes. You have to show that F is continuous as a map of C. So here again, we use Markov process stuff, and I just say very briefly that, okay, it's kind of easy to show that the map that takes a temperature profile T of X to the solution of this equation at a fixed time T is continuous. It's not easy, but it's a kind of standard thing, varying the coefficients in your equation, in a linear equation, and seeing how that impacts the solution at time T. This is it's a nice semi-group, so you can do that. I mean, maybe that's all a bit mysterious, but, and then to turn that into something which tells you the map that goes all the way from T to the steady state of the equation is more complicated. So we need to use kind of crucially that these equations converge exponentially fast towards the steady state. So then we can approximate the steady state by the solution at time T, and we need the rate they converge to be kind of uniform over the set of T, so we can approximate in the same way. So to show that converging exponentially fast to the steady state, we use Markov process stuff, like the same thing, which shows it's well defined, and also gives us exponentially fast convergence. So everything is good. And these two things really don't use the fact that we're in 1D or that we're in a nice simple domain. They would work if we looked even like a non-convex domain in RD with more complicated boundary conditions. They would all still work. Okay, so then we need to show F preserves some complex set. Convex set. So the set we look at is C1 fractionary. So this is a kind of physically natural set. We imagine that our temperature profiles are always trapped between the two boundary temperatures. Okay, so the proof that is in our paper relies very strongly on being in 1D and uses some very just estimates that come out from the 1D problem. But we think we can improve this quite a lot, and we change a bit the set, so it's still something of the form that you're bounded below by some thing that depends on T1 and T2, but isn't just T1. And you're about equally bounded above by something that depends on T1 and T2 that isn't T1, which is kind of weird because I would not have expected your temperature to be able to be, like getting hotter than the hottest wall or colder than the coldest wall at some point. Okay, so I said we're kind of trying to do this in a higher dimensional, more complex domain. So we needed to extend this point. And then we have point 4. We need to show the image of F is compact. You need to show the image of this convex set under F is compact. So this is annoying, all right? So again, we can do this in 1D just by some very explicit computations. Just turn out, we kind of like write steady state of this equation using DuML and then just do some very like nasty bounds of 1D integrals, which is not very difficult. I mean, it takes a while, but it's not, you know, morally difficult. But I don't know, I guess maybe none of you know, but in kinetic theory, you always expect the hydrodynamic quantities, so like the local density, momentum, and temperature to gain some regularity compared to the compared to F. So if F is in LP for some P bigger than 1, then we expect some Hölder regularity for the hydrodynamic quantities or some H1/2 regularity for the hydrodynamic quantities. So this is called averaging lemmas and is used to show existence in all kinds of kinetic equations. So we expect the same thing to be true here, and then this 0.4 we could also extend to the whole space. But you need some LP estimates on the original equation, which is what we can't get. So we show by hand that our temperatures that we get after this map are half Hölder continuous. And then this gives us compactness due to Zero-Scully in the space we work on, but I'm very sure this is true in higher dimensions and in complicated domains. Okay, so it's 12 now. Yeah, sorry for slightly overrunning. Thank you very much. Yeah, well, thank you for the questions anyway.
If you're all out of questions, then thanks, Joe, again. Till for lunch, we'll be back here in an hour for